Hey, this is Mr. Bean. We're doing another lesson in calculus, and today we will be talking about differentiability. Differentiability means that it is possible to take the derivative. That's what the word means, taking the derivative. Let's find out some stuff about this. So the first thing we're going to do is we have a little graph, and I would like you to take just a second, pause the video, and I want you to write in this option number 1 here, what do you think the equation of this graph is? Okay, so use the grid lines here, write down a little equation. Don't cheat, pause and do this on your own. That is very important for your learning. And most of you probably came up with something like this, something where you have this line with a y-intercept of 1 up to over 1. Okay, that's usually what I get from students doing something like this. Now, it's possible that you might have thought, well, hold on, Mr. Bean, you don't even really have a scale on this. Like, how are we supposed to know what's going on with that? So let me show you what the scale is and see if that changes your graph. So 0.003, what does that mean? Every single line is 0.001. Okay, knowing that, why don't you come up with an equation for number 2? Now, what do you think the equation of this thing is? So put that down on number 2. Pause now. There may have been a few of you who came up with this answer, and some of you might mistakenly have put like a 0.0002, but if you think about this, this is to scale, so you're going up 2 lines and over 1 line. It's like a similar triangle, so it would be the same ratio, up 2 over 1, so their slope's still 2. And then the y-intercept is 0.001. Well, here's the thing. That one is not right either. The right answer is this. Y equals sine of 2x plus 0.001. How in the world are you supposed to know that? When you're zoomed in this close, there's no way. You're not going to know that. And so here's what I wanted to be able to show you. Let me pull this up here. Okay, so here's our graph that I have given you. And what I want you to notice is I can start slowly zooming out. So you can see here, I'm going to start to get a little bit better picture. And even if we're zoomed out here so that it's no longer, I'm now to 0.1, it still looks like a straight line. I'm zoomed in really close. So the further out we go, there we go. Now you can see that is a sine curve. So if we go out here and then we can see it. So the idea is if we're zoomed in really, really close to any graphs, if you get really close to this thing, it just looks like a straight line. So that leads us to our definition of the not definition of the derivative, but defining differentiability. So this derivative is going to exist for each point in the domain. So if a function is differentiable, that means we have a derivative everywhere on that function. Another way of thinking about this is that the graph must be smooth, a smooth line or curve, in order for the derivative to exist. So just think about how I zoomed in really, really close on that thing. If it zooms in close and it's a line, that means locally it is a line. It's called local linearity. That phrase right there is an important one. If we zoom in really close, it looks like a line, therefore we can take the derivative. Because what's the derivative? Remember, it's slope. And if we zoom in, we should be able to see that it looks like a line and then recognize the slope of it. Okay, so there are times when a derivative does not exist, when the derivative fails to exist. So when does this happen? The first place that happens is, move this down, on a discontinuity. So if the graph just doesn't exist, whether it's a jump, a hole, a vertical asymptote, anything like that, if the graph stops, then obviously you can't take the derivative of a point right there when there's no graph and if it doesn't exist. Okay, next one. If there is a corner, or another word for that is cusp. So the corner, cusp, we're going to refer to those same things. So what that means is the graph would look something like this. So if I have, a lot of times you'll have a graph that does like something like this and then takes off. If you have some type of sharp corner right there, or an absolute value graph, that's one that you're probably a little bit more familiar with. If you zoomed in on a corner, it's always going to be a corner. We could zoom in, zoom in, zoom in, zoom in, and it's still going to be a corner. You'll never get a straight line. So if you can't have local linearity, there is no derivative. It's not differentiable. So corners and cusps. And then the last one, which is a little bit harder to visualize, is this thing called vertical tangent. So let me show you what I'm talking about. Do you know how in Algebra 1, if you remember, if we had a vertical line, then that has no slope, or in other words, the slope is undefined. We'd say slope is undefined on vertical lines. So if you have some type of graph, like a cube root, where the graph does something like this, and for just a second, just for that split moment right there, the slope right there, just for that moment, is straight up and down. So if you were to draw a tangent line right there, you'd have a vertical line. If you have a vertical tangent line, then the derivative does not exist right there on that point. Okay, so there's our three areas where a derivative would fail to exist. So true or false? Pause and answer these questions. There's your answers. If you have a function that's differentiable, that means it is a smooth curve or line everywhere on the graph. Okay, oops, that's not smooth. So there can be no breaks. Because if we go back to this one, we saw that discontinuities would make the derivative fail to exist. So if it's differentiable, it has to be continuous. Whereas the other way around, just because it's continuous does not mean you have to have a derivative. A good counterexample of this would be that if you have an absolute value graph, that graph is continuous everywhere on its domain, but it is not differentiable right there on that corner. Okay, very, very important true-false questions right here. It may not seem like a big deal, but there will be several questions involved that you've got to be able to answer with those two things. All right, now on to the mean value theorem. I wish we called it the nice value theorem, but it's not called that. Mean value theorem. So what we're looking at is an interval from A to B. So we have some function that's differentiable, and what does that mean? It means we can take the derivative. So if it's differentiable, it has to also be continuous. So it's over some interval A to B, and we're going to say that there exists a point C within the open interval, blah, blah, blah. Okay, let's draw a picture here, and then I'll come back to this. How about we draw something that looks a little bit like a cubic? So if you go like this, and then up and down, something like that. Okay, and let's label this right here A, and we'll do something like this one B. So there's A and B. There's my interval. So what it's saying is that somewhere along the way in here, we're going to have some value C in which the instantaneous rate is equal to the average rate of change. So we have, in other words, the derivative, instantaneous rate of change, is going to be equal to the average rate of change. So we're looking at the tangent line and the secant line. That's what this is saying. So first thing is look at what the average rate of change is. So from A to B, so if we were to draw a line, let's connect those things. Okay, there's our secant line, and excuse me, and that represents, the slope of this represents the average rate of change from A to B. Somewhere along this this graph, there has to be another point. In fact, I'm going to zoom in here so you can see it. There's got to be some point C, at least one point, in which you have exactly the same slope. So let me show you. If I click on this, I'm going to copy this line, and you can see right about there. And I'm going to copy this and drag it, and you can see right about there. So I have, at these 2 points, right there and right there, slope that is exactly the same. So there's actually two values here and here, in which the instantaneous rate of change would be equivalent to the average rate of change. Okay, I may have lost you on this, but let's just jump into an example. Hopefully this will help. So here I have our example. We're going to use this to find, using the mean value theorem, we're going to find a value C on this interval 4 to 6. Now I've drawn a picture here. You can draw this on your notes as well if you would like to. You will not need to be drawing pictures of the graphs. You don't need to draw the graph on your assignment, but I find that it helps. It is really important for us to recognize what we're doing every time we plug a number in. So the first thing for mean value theorem is the mean, average, let's figure out the average rate of change on the interval. We did this a whole bunch before. So let's plug in f of 4, get what that equals, and we'll plug in an f of 6 and get what that equals. All right, there we go. I came up with when you plug in a 4, you get a 6, and when you plug in a 6, you get a negative 2. Again, I'm just using the function. So remember, whenever you plug something in, you've got to think, what am I about to get as an answer? If you plug a number into a function, you get a y value. I know that seems so obvious and easy, but you have to do it. Every time you plug something in, what are you about to get? A y values. All right, now let's get the average rate of change. So we get, let's do 6 minus a negative 2 means 6 plus 2. So there's my two y values. My two x values are 4 and 6. So I started with the 6, got to start with the 4 here. So 4 minus 6, that gives me 8 over negative 2. So my average rate of change on the interval is negative 4. That is the slope. Okay, so save that there. Let's keep it. And actually, you know what I'm going to do? I'm going to show you something here. Okay, so what was my slope? My slope of the secant line was negative 4. What I'm showing is that from 4 to 6 is the interval. So I'm going from here to here. Those are the 2 points that I just figured out from those 2 points on that interval. So there is the secant line, and the slope would be negative 4, just like what we figured out. The next thing we'll need is now we're going to find some value of c in this interval. So somewhere along this interval between 4 and 6, there is a point along the graph where the instantaneous rate of change equals the average. So in other words, there's my average, negative 4. I want to find a tangent line slope that is also negative 4. So you're just trying to see a parallel line to the secant. Can you see it? I think it's probably going to be somewhere right around here, if you can think about it. So I'm going to zoom in on this. Let's zoom in. Okay, so I changed the scale a little bit. I'm zooming in. It's still exactly the same interval. This is the same graph from 4 to 6. On that, this just helps us see a little bit better. So what am I looking for again? The slope is negative 6. So when is the instantaneous rate of change? That's the derivative. That's why I gave you that. So when does the instantaneous rate of change equal? Oh, I said negative 6. Negative 4. Equal negative 4. And then you solve. Negative 4x equals negative 20. So x equals 5. So our value of c that's inside this interval is right here at 5. Okay, it was just a coincidence it was right at in the middle. So if we came up here and put on found the graph, that instantaneous rate of change, can you visualize it? That tangent line would be parallel to the secant line. It would have the same slope. So here's your picture of that. All right, that's how you use mean value theorem. Next, we're going to use our calculator. So let's pull out your graphing calculator. You're going to need that on this part of the lesson, so please go grab it. Pause if you don't have it yet. And if you don't have a TI-84 or 83, that's okay. You can still do this, but you're going to have to look it up in your user manual how this all works. Because I'm not going to show you all the lessons on how to do every single calculator. So this is really nice trick though. When you can use a calculator in calculus, on portions where you need to find the value of the derivative, okay, we have some original function, and you will actually be able to take the derivative of this soon. But for now, this is going to be really complicated to take the derivative. So what we're going to do is, and plus plugging in that number, I mean, that's going to be a pain. So we are going to tell the calculator to do it. Here's how we do it. If you look at math, and then you scroll down to option number 8. We're going to use options 8 and 9 quite a bit this year. So 8 is the derivative, 9 is for an integral, second half of calculus. We'll talk about that later in the year. So math 8 and math 9. So math 8, and that's going to give us this screen right here. And I'm going to, I made a copy of this one over on my notes. Okay, so you get this weird syntax. Again, this is for the TI-84. And what you're going to type in here is you'll put the variable x right there. So that's where x goes, because it's going to be, so this is what it should look like. D of dx. And then here, this is where you put f of x. So in this case, it would be x cubed over the natural log of x. So you type that whole thing into that space. Then you arrow over here. And then this is at what value are we going to take the derivative. When are we evaluating this? And it's at 0.057. So here you put into that box right there, you're going to put 0.57. Zoom in here and you can take a look. So when you hit enter, it is going to automatically figure out what the derivative is and then plug that number in. Oh, that is so nice. So that means, let me take a screenshot of that, drag it over. Let's get rid of that. And there we go. So we would have the answer is, f prime of 0.57 is negative 2.762. Remember, we go 3 decimals. All right, so that just means, again, you got to think about every time you plug something in, at the x value of 0.57, the slope of the tangent line, or the instantaneous rate of change of that graph, is going to be negative 2.762. Pretty easy stuff, but you're going to have some practice just to make sure you get used to plugging those numbers in. Okay, on to the last part of the lesson. This is actually one of my favorite things in all of calculus. I love this stuff. It is a little bit challenging for some people, so you just got to really try and listen to this part. I'm hoping to make this as easy as possible. We're going to relate the graphs of a function f and its derivative f prime. We're looking at the graphs of both the function and the graph of the derivative. Okay, that does sound a little bit weird to try and think about the graph of a derivative function. What's the graph of the slope? Well, here's what we'll do to figure it out. You take the function f and you focus on the slope. So as I look at the slope of this, my slope is positive, it's going up, and then my slope stops and turns around, and now the slope's negative, and then it grows up and the slope is positive. So the slope of f is the y value of f prime. Let me say that again. The slope of f is the y value of f prime. So let's talk about what this slope is. This is positive. Is it a little bit positive? Is it really, really positive slope? This is really, really positive slope. Let's use a different color. Okay, really big positive slope. And as we get closer up here, it's really, really little positive slope. It's still positive, but it's slowing. It's not quite as big as it was down here. This is big positive. And then right here at the peak, what's the tangent line slope right there? It would be horizontal. So the slope right there is 0. And then here it's just a little bit negative. So I'll put a little negative. And then here it's a little bit more negative. So I'll put a little bit more negative. And then here it's a little bit negative. And then when we get down to this valley, right there, the slope is 0. And then here the slope is a little bit positive. But over here the slope is really positive. Okay. So think about through this, what would the graph look like? So if I had to sketch it, I'm going to start with the zeros. The slope of f is the y value of f prime. So in green, for my graph in blue, I should say, I'm going to graph f prime in blue. So right here, we are going to put a dot, because if the slope is 0, it's the y value of f prime. And then here, it's also going to be a dot. Okay, so slope is 0, dot, and dot, right on the x-axis for my f prime. Then what? So the y values here are positive. In fact, here, it's really positive. So I'm going to come way up here. It's really, really positive. And then here, it's just a little bit positive. So that means it's just a little bit positive right here. Okay, what about here? Here, it's a little bit negative. Here, it's a little bit more negative. So this is the most negative it's going to be, is down here somewhere, maybe. And then it's going to slowly get a little bit less negative. So think about this until we get back to 0. And then here it's really positive again. So what you're getting, if you can see in blue, we're going to get something like this. This is the slope graph. The graph of what the slope is of our original function. That's the graph of the derivative, what I have in blue. Okay, what you're going to do on your practice, you won't have to graph it from scratch. That's pretty difficult and challenging. What you're going to do is I'm going to give you a bunch of functions that are f prime of x and a bunch of functions that are just regular old f of x. And you got to figure out which ones match together. Just remember, this is going to take some practice. It will not come to you right off the bat for most of you. Think the slope of f is representing the y value of f prime. Okay, hey man, we are done with Unit 2 now. I'm going to leave you until we get to Unit 4, so good luck with Mr. Brust. And when I say good luck with Mr. Brust, I really mean good luck with Mr. Brust. Hopefully you survive that next unit, and I'll catch you back here. Rock that master check.